Okay, let's talk about acceleration and mass and acceleration and moment of inertia. And so let's start out talking about a linear version here. And so if we just have a mass m and I put a net force on it, so there's some kind of net force on this mass, then we know the object is going to accelerate according to this function. The net force divided by the mass in kilograms, force in newtons, gives me the acceleration meters per second squared. The bigger the mass, the harder it is to accelerate the object. Mass and acceleration are inverse of each other. Small mass means it's easier. Well, down here when we rotate things, let's just take a meter stick, and let's say there's a meter stick, and I'm going to pivot it. I'm going to take it and pivot it in the middle. I'm going to rotate it counterclockwise. All right. So I got a little pivot in the middle here. You can see the dot right in the middle. So if it's a meter stick, that means from the pivot point to this mass is real important, because moment of inertia, I'm going to go ahead and write that down here, moment of inertia, also called rotational inertia or angular inertia, is related to the distribution of the mass. In other words, the mass that's on this meter stick, I have two little masses out here on the end, and where those masses are located on that meter stick is what's going to determine how hard or how easy it is to accelerate it in a circle, angular acceleration. So this right here is going to be 0.50 meters. And from the pivot point to this one is also going to be 0.50 meters. Obviously not drawn to scale, but those two are the same if that's in the middle. And it is. And so that's going to rotate angular rotation according to this function. Angular rotation, radians per second squared, is equal to the net torque divided by I. This I is what we call the moment of inertia, or rotational or angular inertia. So, depending on the size of I is going to tell me how hard it is to accelerate this object in a circle, angular acceleration. So how do I find I? Well, for this kind of deal here, I is equal to the distribution of the masses, which means I'm going to sum up all the mr squared. Well, how many m's do I have? I have two. They're both 0.5, so I will equal 0. Sorry, not 0. Erase that. There we go. I equals 1 kilogram. I'm going to say these masses up here are 1 kilogram. I didn't get that. This is 1 kilogram. That's 1 kilogram. So 1 kilogram times how far away is that mass from the pivot point? 0.50 meters. I'm going to square that number. 1 kilogram times 0.5 meters squared gives me 0.25 kilograms times meter squared. I have another one I'm going to add. That's what the sigma means, add. It's going to be 1 kilogram. Does it have to be 1 kilogram? No, I can put a 2 kilogram mass over there. In this case, I got two 1 kilogram masses, both 0.5 meters away from the pivot point. When I do that, I'm going to get I equal to 0.5 kilograms times meters squared. That's a number, and that number tells me something about how hard or how easy it is to accelerate this thing, this meter stick, in the counterclockwise direction. Well, now let's say that I do this. Let's say I come up here, and let's say that I move these masses where they're only about 0.3, all right? So the masses are about 0.3 meters from the center now. So in other words, the distance from here to here, I'm going to say is 0.3 meters. And the same for this one. We'll make it the same. Doesn't have to be the same. That's what I'm doing. All right? That's what I'm defining. So I equals the sum of them r squared. Well, now I've got 1 kilogram times 0.3 meters squared plus 1 kilogram times 0.30 meters squared. When I do that, 0.3 squared plus 0.3 squared gives me 0.18. So I equals 0.18 kilograms times meters squared. That number's smaller than the original number I gave you, the 0.5. That means if I move these masses closer to the middle, it becomes easier to accelerate it with the same torque, with the same amount of torque. Just like if this mass gets smaller, it becomes easier to accelerate it in a linear fashion with the same net force. So that's moment of inertia and how it affects the angular acceleration of a rotating object. And that's that.